Inspection and testing is covered in Part 6 of the 17th edition wiring regulations. Interestingly, it's less than 10 pages long in a very thick document, and yet it's a part which has incredible importance.
Yes, although only a very small part in the regs, it's more than likely the most important part of the installation process. And as the title implies, it comprises of two equally important parts, an inspection part and a testing part.
The actual inspection and testing process, including important safety considerations, are covered in a range of other videos. In this video, we're going to focus on one of the core parts of the inspection process, the Schedule of Inspections in Appendix 6. This is now only used for initial verification in conjunction with an electrical installation certificate, as Amendment Number 1 of the 17th edition introduced a new report form and inspection schedule for periodic inspection and testing. So Tony, the first question is, what is the Schedule of Inspections and why do we need it?
The schedule of items inspected lists all of the critical items that need to be checked during the inspection process. While it's a neat ordered format of the inspection requirements listed in section 611 of the regs, it is not intended to be an order of inspections to be followed precisely, and indeed it would be impossible to do that. However, the inspector must realise that upon completion they will have covered and checked all of the items.
Now I know we covered the inspection process elsewhere for initial verification, but I think it's important to point out when you'd actually fill in the boxes on the schedule and what you'd write.
I would normally refer to the schedule throughout the whole process. With initial verification, this will be ongoing throughout the erection process, using the schedule of items inspected as a checklist. However, I would not actually mark any of the boxes until the installation is complete.
And what goes in the boxes?
I would expect either a tick in every box or NA, not applicable, depending on the type of installation.
There are 5 main headings on the Schedule of Inspections. The first is Protective Measures Against Electric Shock, which, so you're aware, is titled Methods of Protection Against Electric Shock on the schedule shown in the regs. Then we have Prevention of Mutual Detrimental Influence, Identification, Cables and Conductors, and General. Under each heading are a number of items to be checked throughout the installation.
One important thing to point out is that some certificates, such as the Domestic Electrical Installation Certificate, have a reduced number of items because they only include those items relevant to that type of installation.
In this video, we'll work through a schedule on the full Electrical Installation Certificate. We'll visit a number of locations where we can examine what the items listed on the schedule are and what may need to be considered. So I'll catch up with you later, Tone. Under Protective Measures Against Electric Shock, there are several subcategories, including Basic Protection, Fault Protection and Additional Protection. These are terms used primarily in Chapter 4.1 of the regs, Protection Against Electric Shock. Chapter 4.1 outlines 4 protective measures generally permitted to provide protection against electric shock. It is within these protective measures that we can see reference to requirements for basic protection, fault protection and additional protection. The terms basic protection and fault protection are defined in Part 2 of the regs. In its simplest form, basic protection is insulation which is applied to live parts, so preventing contact with live conductors. And fault protection will most commonly involve, for example, protective earthing and a means of automatic disconnection of the supply for single fault conditions which could cause exposed conductive parts to become live. Additional protection is not defined in Part 2 of the regs, but is detailed in Section 415. Additional protection against electric shock can be provided by either supplementary equipotential bonding or RCD protection, using an RCD with a residual rated operating current not exceeding 30 milliamps, which is becoming the preferred choice. The first item on the schedule is for protective measures against electric shock, which incorporate both basic and fault protection.
Under basic and fault protection, we first have the protective measure extra low voltage provided by SELV and PELV. These two protective measures are very similar. In this diagram we can compare SELV and PELV. In this case, the extra low voltage source is a safety isolating transformer. The circuit diagram shows that for SELV there is no earth provision on the secondary side of the transformer, whereas with PELV the earth provision continues through to the load side. So when it comes to inspection, there are several things I need to check. The first of these is, does the location I'm in this case a bathroom, have requirements for SELV or PELV?
It is part 7 of the regulations where you'll commonly find reference to requirements for SELV and PELV. For example, in a room containing a bath or shower, suitable fixed current using equipment can be installed in zone 0 if SELV is used, but not PELV. The SELV source being located outside the zones.
So once I've established that there is a requirement for SELV or PELV, and indeed that one of these is being used, I need to check which is being used and that the source of extra low voltage is acceptable.
Section 414 of the 17th edition lists 4 acceptable sources for SELV or PELV. The most common of these is by safety isolating transformer, as we've already seen. But in industrial or similar locations, it could also be provided, for example, by a motor-driven generator.
A common mistake with the installation of SELV equipment occurs when metallic fixed equipment on the secondary side is wired using standard twin and CPC cable. Now, I've seen jobs where the electrician has not only connected the CPC to the transformer on the primary side, but also where they've made a connection to the fixing screws or similar at the equipment. This effectively turns SELV into PELV and will breach requirements where only SELV is acceptable. So with SELV circuits, you would not expect to see circuit protective conductors terminated on the secondary side.
Our next protective measure, featuring aspects of both basic and fault protection, is double or reinforced insulation. In the 16th edition, this was called use of Class 2 equipment. This protective measure is generally applicable only to individual items of equipment, such as luminaires or space heaters. This protective measure is applicable in all situations unless limitations are given for some special installations or locations in Part 7. In practical inspection terms, you'd be checking to see if equipment has double or reinforced insulation. Sometimes it's as easy as looking for the familiar double square symbol on Class 2 equipment, but reinforced insulation is a little trickier.
Well, although this appeared in the definitions of the 16th edition, it didn't appear on the schedule of items inspected, whereas in the 17th it does. Reinforced insulation is effectively insulation either in single or multiple layers, which gives equivalent protection to that of double insulation.
If you're uncertain whether insulation is double or reinforced, always consult the manufacturer, or where applicable, the designer. And if double or reinforced insulation is being used as a protective measure, it's important to check that no damage is evident. Moving on to the next heading, we have methods of protection against electric shock incorporating only basic protection. And the first of these is insulation of live parts.
Quite a simple one, this. Throughout the installation process and upon completion, it's important to check that any parts of the installation which will be live during service have not received damage to the basic insulation protecting live parts. For example, when installing cables, they can be damaged in a number of ways.
And what are some of those ways, Tony?
A common example can be damage to the cables caused by being pulled across sharp edges of trunking or basket systems, especially where the edges have not been deburred properly. Another one is where a cable is being run through holes in joists, already containing other cables. If it's pulled through too fast, the friction can cause the sheathing and in extreme cases, the insulation on the existing cables to chafe or even melt, exposing the live conductors.
Next, we move to barriers or enclosures. Examples of these would be trunking, conduit, distribution boards and control panels.
There are two main issues here. First, is the barrier or enclosure suitably selected for the environment and external influence in which it's operating? In this case, dust. Reference to section 522 and appendix 5 of the regs is essential here. And if you're in a special installation or location, some of the requirements in part 7. Secondly, barriers or enclosures need to provide suitable protection for persons against contact with hazardous parts inside the enclosure.
In order to confirm that the necessary level of protection has been afforded, knowledge of IP and similar codes will be necessary. For example, it's generally considered that the minimum level of protection required to prevent fingers touching enclosed live parts can be provided by IP2X or IPXXB equipment, with certain exceptions.
The trouble is that unless you have the official British standard test finger with you, the suitability of IP ratings is hard to guarantee. So we have to take a common sense approach. It should be possible to confirm by thorough visual inspection that we have the necessary degree of protection to protect against the ingress of fingers or other solid objects in any enclosure. For a domestic consumer unit, the top should be a minimum of IP4X, that's no holes bigger than 1mm, and the sides and the front should be a minimum of IP2X, that's no holes bigger than 12.5mm, and also no deeper than 80mm into the enclosure. Now I would say that in real common sense terms, with kids around, that any hole that big should be avoided.
The next two items on the schedule under basic protection are obstacles or by placing out of reach. There are two asterisks next to these on the NIC-EIC schedule of items inspected. These remind us that these protective measures are only for use in installations controlled or supervised by skilled persons. A common example of by placing out of reach would be the exposed conductors supplying an overhead travelling crane.
I've actually seen this box ticked on the schedule because the electrician mistakenly thought a consumer unit or a distribution board mounted at high level was an example of placing out of reach.
Have you seen examples of obstacles?
Obstacles is not so common. In fact, in all my days, I've only encountered this type of protection once, and that was in a very old switch room with exposed live parts along one wall, and the obstacle was just a set of railings.
If you do encounter these protective measures, you should first be checking they're actually there as part of the intended design, as the use of insulation and barriers or enclosures should be the preferred option. Once this is ascertained, it's necessary to check that the clearance distances required for these measures have been achieved, not forgetting that the designer may need to increase distances to allow for long or bulky objects such as aluminium ladders to be handled. Our next subheading under protective measures against electric shock includes the protective measures which incorporate fault protection. The first of these is automatic disconnection of supply, sometimes referred to as ADS. For this protective measure to be effective, it requires protective earthing, as illustrated in figure 2.1 of the regs. The first check is for the presence of an earthing conductor. This conductor connects the main earthing terminal to the means of earthing. It's important to point out that this is just an inspection at this stage. Before the supply is connected, the continuity of all protective conductors is verified by testing. Now, as well as checking the presence of the earthing conductor and that it's suitably connected, it's important to check its cross-sectional area is suitable for the installation. The size of an earthing conductor is usually selected from Table 54.7 of the regs, or Table 54.1 if the earthing conductor is buried. Similarly, the presence of circuit protective conductors needs to be checked, and where they are required, that they've been properly selected and installed. Don't forget here that we could be checking circuit protective conductors provided by twin and CPC cable, the metallic armouring of a steel wire armoured cable, or the metallic enclosure of conduit or trunking. Whichever type of circuit protective conductor is used, It must meet the requirements of section 543 of the wiring regulations.
Next, we have the presence of protective bonding conductors. These connect from the main earthing terminal to extraneous conductive parts, for example gas or water pipes, which may introduce earth potential into the installation. It is important to check that the connection to any pipework is on the installation side and not on the supply side, and is made as close as possible to where that supply enters the premises. Where practical, this should be made within 600 millimetres of the meter outlet before any branch pipework, or at the point of entry to the building if the meter is external.
In terms of sizing, except where PME conditions apply, a main protective bonding conductor must have a cross-sectional area not less than half that required for the earthing conductor of the installation, and not less than 6 mm squared. Where the bonding conductor is of copper, its cross-sectional area need not exceed 25 mm squared. If the installation supply system is TNCS, which adopts a PME, protective multiple earthing system, then the bonding conductor should be sized in accordance with table 54.8. Next, we have the presence of earthing arrangements for combined protective and functional purposes. In a situation where a designer knows the intended use of a building, for example in an office, it's easy to predict that there could possibly be a large number of devices, such as PCs, which produce protective conductor currents on the earthing system for functional purposes, usually power supply smoothing and interference suppression. So the protective earthing installed for safety purposes, by default, also acts as a functional earth. The requirements for this situation are covered in section 543.7, earthing requirements for the installation of equipment having high protective conductor currents.
Easy enough if you are designing an office, and during inspection you'll be looking for socket outlets which have two separate earthing terminals rather than the one that you would normally expect. So what about in the home? It's important to assess whether the designer has considered if high integrity earthing is required for the socket outlets.
The regulations require that every final circuit and distribution circuit supplying either one or more items of equipment such that the total protective conductor current is likely to exceed 10 mA shall adopt a method of high integrity protective connection.
So it's not unreasonable to assume that on a ring final circuit with lots of equipment that the 10 mA level could be exceeded, and the requirements of regulation group 543.7 would have to be considered.
The next item is presence of adequate arrangements for alternative sources where applicable. This is referring mainly to standby or backup power supplies. The adequate arrangements are described in section 551 of the wiring regulations, particularly regulation group 551.6. Here, isolation and switching requirements are given to prevent the alternative source operating in parallel with the system for distribution of electricity to the public.
If there are alternative sources of supply for an installation, it's important to issue two sets of documentation: a certificate, together with an inspection and test schedule for the public supply, and another for the standby power supply.
The next provision against electric shock is FELV. The term FELV is used to describe any extra low voltage circuit that does not fulfill all of the requirements for SELV or PELV circuits. In practical terms, the most common cause of FELV not fulfilling SELV or PELV requirements will be that the extra low voltage source is not appropriate for SELV or PELV, so for example, not a safety isolating transformer. In a FELV system, extra low voltage is used for purely functional reasons, although its use may have safety benefits. FELV circuits need not be electrically separated from earth or other systems, and FELV circuit conductors need not be physically separated from those of other systems. An example of where FELV might be used is in the control, interlock and contactor start circuitry for a motor.
If you do encounter FELV, it's essential to make sure that the primary circuit is protected by automatic disconnection of supply, ADS. And the final word on FELV is it can no longer be provided by means of an auto transformer, as was allowed in the 16th edition.
The final item, under the subheading of Automatic Disconnection of Supply, is choice and setting of protective and monitoring devices for fault protection and/or overcurrent protection.
So, we are concerned with fuses, circuit breakers, RCDs and any current monitoring relay which controls separate circuit breakers. Here again, we're checking the choice and setting against those of the design. With fuses and circuit breakers, this will be the rating, type and characteristics of each device. Devices which have adjustable current settings and also time current characteristics, such as some types of MCCB, may require additional attention.
The next two protective measures, non-conducting location and earth-free equipotential bonding, are quite rare and again are only used in controlled supervised conditions. For example, some specialist testing used in manufacturing locations. So for most installations, you would expect to have to write an NA here, and the topic really falls outside the scope of this video. The final protective measure listed under fault protection is electrical separation. The principle of electrical separation is very similar to SELV, but do not confuse the two. SELV is extra low voltage, whereas electrical separation can be up to 500 volts.
The most common example of electrical separation is the electric shaver socket. During inspection, we need to check that the source is an isolating transformer complying with BSEN 61558-2-5, of which the secondary winding is not earthed. Where electrical separation is used to supply an individual item of equipment, the inspector should verify that no exposed conductive parts of the separated circuit, such as any metal casing of an item of equipment fed by the circuit, is connected to the protective conductor or exposed conductive parts of another circuit or to earth. On the schedule there are two boxes under electrical separation. One for where one item of current using equipment is connected, which is the most common, and the other for when more than one item of current using equipment is connected to the same source of electrical separation. This second option is only suitable for use in installations controlled or supervised by a skilled or instructed person, and this would need to be checked.
We now have our final subheading under protective measures against electric shock, additional protection. As mentioned earlier, this refers to the presence of residual current devices and, where required, supplementary equipotential bonding. Now, additional protection by an RCD having a rated operating current not exceeding 30 milliamps is a requirement seen many times throughout the regulations. But what does it mean, Tony?
It is intended as additional protection in the event of failure of the provision for basic protection and/or the provision for fault protection, or carelessness by users. It's specified many times in Part 7 and some other parts, but it always refers you back to the detailed requirements in Section 415. The inspector will need to verify that the RCD protection specified in the design is appropriate for both the type and construction of the installation and its intended use.
So you need to be very familiar with the requirements in the regs for RCDs when deciding what you're going to put in the box, and indeed, as we'll see shortly, which box. It's also important to differentiate between RCDs which are intended to provide additional protection against electric shock, having a maximum operating current of 30 milliamps, and those which may be selected to provide fire protection, which is, for example, a requirement in Section 705, Agricultural and Horticultural Premises, where the maximum operating current must not exceed 300 milliamps. Section 705 is also an example of a special installation or location requiring additional protection by supplementary equipotential bonding. Indeed, it is in Part 7 of the wiring regulations where you'll find specific requirements for supplementary equipotential bonding, and the locations covered all have an increased risk of electric shock. Although you can still find supplementary equipotential bonding in other locations. For example, in situations where, for whatever reason, automatic disconnection of the supply cannot be achieved in the required time laid down in the regulations. For inspection purposes, the main concern is to establish whether there is a requirement for supplementary equipotential bonding, and if there is, make sure it exists.
Most of the requirements for supplementary equipotential bonding was removed from the regs when the 16th was introduced in 1991. The most common requirement removed was the bonding of a kitchen sink. If you find supplementary equipotential bonding and there isn't a requirement for it, then it isn't a problem. However, copper cable isn't an abundant resource, so it's a shame to waste it unnecessarily.
We've now finished an overview of the items which are under the heading Protective Measures Against Electric Shock. This is an important part of the inspection schedule which is sometimes not given the attention it's due.
The reason is that probably people are put off by the title.
So what does it mean then, Tone?
The word you need to look at, Dave, is detrimental. What would be detrimental or harmful to the electrical installation?
For the first box, proximity of non-electrical services and other influences, the inspector is really checking that there's been communication between the electrical installation designer and anyone involved with designing other parts of the installation, for example, production plant and services.
The inspector needs to verify that there are no harmful effects either happening or that could happen to degrade the effectiveness of electrical equipment.
Harmful effects could be caused by heat, steam, smoke, condensation, or fumes from non-electrical services. Or, for example, by cables with thermoplastic sheathing coming into contact with polystyrene, which is sometimes used as a thermal insulation material.
It's important to say that the schedule does say mutual, so the electrical system should not interfere with the operation of other systems, for example, communication systems.
A classic example is making sure that no electrical cables are run in a lift shaft, unless they're part of the lift installation. This leads us on to the next box, segregation of band 1 and band 2 circuits or band 2 insulation used. Now, this is concerned with circuits of different voltages being contained together within the same wiring system. This is because some band 2 cables may have insulation rated at a much lower voltage than, say, a cable in a band 1 circuit.
Band 1 and 2 circuits can only be contained in the same wiring system if one of the installation methods listed in Regulation 528.1 is adopted. For example, being run in a separate compartment, or if both circuits have insulation rated at highest voltage present. Where segregation is by a partition, the inspector needs to check that the partition is maintained throughout the length of the circuit if required, and if the partition is metal, it is earthed.
With the next box, segregation of safety circuits, the inspector is making sure that these are segregated from other circuits and from each other. This typically means separating by a suitable distance, or more usually by use of separate enclosures, compartmental trunking, or one of the other methods detailed in Regulation 528.1. When designing the installation, the designer would have considered the protection of the safety systems from any electromagnetic interference. If special requirements have been specified, such as metallic shielding and certain types of trunking, then the inspector needs to verify that this exists. This section of the schedule has 4 items. The first is presence of diagrams, instructions, circuit charts and similar information. Under the 17th edition, documentation for the electrical installation is a requirement of Chapter 1.3, Fundamental Principles. Depending on the size and nature of the installation, there are many types of information which may be required. The requirements for diagrams are specified in Regulation 514.9, but this doesn't just mean drawings. It can be a chart, table, or similar form of information. For a domestic installation, a copy of the circuit schedule within or adjacent to the consumer unit would be sufficient. But in an industrial situation, as well as circuit schedules, there may be quite a large dossier, including important information about protective measures, all points of isolation, and also example details about wiring systems used throughout. It's worth mentioning here that all NIC EIC certificates have a separate circuit details section. This itself could be placed at distribution boards to meet these requirements. Alternatively, there are also available circuit detail labels which provide a neat solution. The next item, presence of danger notices and other warning notices, requires the inspector to not only check their presence but also their durability. These include warnings about the presence of voltages on enclosures which contain live parts, the presence of circuits which may have high protective conductor currents, mix of new and old cable colours, and labels warning that isolation may be required. Isolators themselves may need to have identification if there could be any confusion as to what equipment it isolates. Other labels required include the inspection and testing reminder, and also the presence of RCDs, and that they require manual testing. Finally, a very important label is one warning of dual supplies. As microgeneration becomes more adopted, we will see a wider use of these. Next, we have labelling of protective devices, switches and terminals. And here we're checking again that where required, identification is present. Except where there is no possibility of confusion, all switches and devices for controls should have a suitable means of identification to indicate its purpose and the installation or circuit it controls. For some complex installations, where the arrangement within equipment does not identify the wiring sufficiently well, it may be necessary to identify the terminations of the conductors using a number or a code. Finally, under identification, we have identification of conductors. It must be obvious to see if a conductor is a line, neutral or an earth, and whether the polarity is correct at terminations. However, if it's not obvious, then additional identification must be adopted, and if it's used, the inspector should double check it against the circuit schedules and diagrams. First, under this heading, we need to check the selection of conductors for current carrying capacity and voltage drop. At this stage, we're checking them against the installation design information to verify they've been selected and installed as the designer intended.
When installing any circuit, it is vital to check whether it comes into contact with thermal insulation. And if it does, was this taken into account by the designer, as this could drastically reduce the current carrying capacity of the cables.
This is a common oversight when installing standard ring and radial circuits, which are detailed in Appendix 1.5 of the regs, and could mean that cable sizes may have to be increased.
With regard to voltage drop, I would advise a practical approach. If you see a long cable run, which is going to supply a heavy load, then voltage drop could be an issue, and so may require investigation. The acceptable percentage values for voltage drop are detailed in Table 12A of the regs.
Next, we have erection methods. What can you tell us about this, Tony?
Here we are checking that the installed cables and conductors meet the requirements of Chapter 5.2 of the regs. Some of the issues we've already encountered for other items on the schedule, but we are verifying that the cables meet the required standards and that the installation process has not compromised their safety or intended use in any way. Things to look out for include the grouping of cables in trunking, that supports are at the correct spacing and are suitable for where they're going to be located, and that the radius of bends is not less than the minimum recommended.
The next three headings relate to the requirements of Regulation Group 522.6, which focuses on minimising damage arising from mechanical stress, examples of which could be caused by impact, abrasion, penetration, tension or compression during installation, use or maintenance.
The regulations within 522.6 apply to protection of cables when installed under floors, within ceiling voids, walls, and also partitions with an internal construction which could include metallic parts.
It's worth saying that this group of regulations contains some dramatic changes to previous editions of the regulations and should be studied in some depth, as detailed knowledge will be required to know whether a tick or NA not applicable is relevant for each box. The box routing of cables in prescribed zones is referring to cables run in the zones as seen in this diagram.
From the diagram, you'll notice that the prescribed zones are horizontal or vertical from any point or accessory, 150 mm from any corner of any wall, and 150 mm down from any ceiling.
The next box requires the inspector to check that the wiring system incorporates an earthed armour or sheath, or is mechanically protected against the penetration of nails, screws or the like.
And it's worth mentioning here that metal capping will not provide that degree of protection. Metal capping is there to protect the cable from the plasterer's trowel.
The final box of R3, which are the concern of Regulation Group 522.6, is the one which requires the inspector to check that 30 mA RCD additional protection has been provided for cables concealed less than 50 mm from the surface of a wall. This will only be required in a premises not under the supervision of skilled or instructed persons, and if one of the other protective options listed in Regulation Group 522.6 have not been used. When filling in this box, it's a good idea to cross-check with the other box we saw earlier with regard to RCDs for additional protection, as a cross in one may mean in some situations that a cross is required in the other. Next, we have connections of conductors, and here the inspector needs to check that every connection is sound, both mechanically and electrically.
This is vital, Dave. The most causes of fires are loose connections.
Absolutely. Part of this is also ensuring that all connections in a wiring system are accessible for future inspections.
The method of connection should take into account external influences, such as moisture and vibration. Additionally, there should be no strain on cable terminations, and where cables enter an enclosure, the outer sheath, intended to provide a degree of mechanical protection, should also enter. So I wouldn't want to see the cable coloured cause as it is here.
Presence of fire barriers, suitable seals and protection against thermal effects is fairly self-explanatory. Where wiring systems pass through walls, it is vital that any gap surrounding them, and also any gap within them, which could allow fire to spread from one part of a building to another, is filled or blocked with an appropriate material having a fire resistance of no less than that of the surrounding building material concerned. The internal use of a fire barrier may not be necessary if a non-flame propagating wiring system is used.
It's worth mentioning here that there's a new best practice guide from the Electrical Safety Council, which examines electrical installations and their impact on the fire performance of buildings.
With regards to thermal effects, a typical example to check for is that the heat-resistant sheathing, provided with some type of light fitting, have been fitted to the cables entering the luminaire, so protecting the supply cable from the heat of the lamp. The check for fire barriers and sealing would be an ongoing check during building construction. We now enter the final section on the schedule, which picks up on the general items. The first of these is presence and correct location of appropriate devices for isolation and switching. Now again, this goes over some of the detail the inspector will already have checked, for example under labelling. But of incredible importance here is actually checking that any device installed for isolation, switching off for mechanical maintenance, emergency switching and functional switching is actually suitable for this purpose. Table 53.2 of the 17th edition provides handy information for checking the suitability of different devices. The next item is adequacy of access to switchgear and other equipment. This is referring to the access required for future maintenance and similar activities, including periodic inspection reporting, and is a requirement of Regulation 132.12. But a good source of information on adequacy of access is provided in the Memorandum of Guidance for the Electricity at Work regulations, which also lists sufficient lighting as a requirement. Next, we have particular protective measures for special installations and locations. Now, we've mentioned some of these before, but the inspector must carefully examine all of the special locations and installations within the particular premises being inspected and verify that any required protective measures have been adopted. Don't forget that many smaller commercial and industrial premises will not have any special locations or installations whatsoever.
The item, connection of single pole devices for protection or switching in line conductors only, is a visual check to verify that all single pole switching and control devices are connected in the line conductor only. Don't forget that this check is an addition and not an alternative to the required polarity tests.
The next item, correct connection of accessories and equipment, would be inspected at the same time as a number of other items we've seen. For example, connection of conductors. Again, we're checking that conductors are connected to the correct terminal and that the terminations are both mechanically and electrically sound. Next, we have presence of undervoltage protective devices. Here, the inspector is checking that the requirements of section 445 have been met. For example, that suitable precautions shall be taken where a reduction in voltage, or more commonly, a loss of supply and subsequent restoration of that supply, could cause danger. The inspector should check that any undervoltage devices installed, usually in motor starters and control equipment, conform to the design requirements for that particular part of the installation.
Selection of equipment and protective measures appropriate to external influences is another item we have touched on elsewhere, for example in the section on barriers and enclosures. Again, the inspector needs to consider the external influences that are reasonably likely to occur during the lifetime of the installation. And take into account climate change, anything is possible with equipment situated outside.
The range of external influences would have been determined by the designer in accordance with Part 3 of the Regs Assessment of General Characteristics.
Sometimes, to achieve the level of protection required against external influences, it may be necessary to build additional housing around the electrical equipment. If this is the case, it should be checked that this extra housing will not cause overheating of the protective equipment, impair its operation, or impede access for inspection, testing or maintenance purposes.
For many installations, it's actually during the construction process that they'll be subjected to a higher risk of mechanical damage and external influences, such as dust and water, than they will during their normal working life. So the inspector should check for this damage before equipment and cables are concealed, and ensure that they're replaced if damaged. We now reach the final item on the checklist: selection of appropriate functional switching devices.
Functional switches are devices that are intended to switch on or off, or in the case of a dimmer, vary the supply of electrical energy to all or part of an installation for normal operating purposes. Again, table 5.3.2, which we referred to earlier when checking devices for isolation, can also be referenced to here for the suitability of any device for functional switching.
We've seen that the schedule of inspection is quite an in-depth subject, which, although arranged into a neat checkbox style list, is not a checklist which the inspector can work through sequentially.
Although it looks like the football pools, it's not just any random 8 from 10. You've got to take extreme care with your entry. And when you're actually inspecting, you'll be cross-referencing between sections all the time. And in some cases, your inspection will be focusing on a number of the boxes at the same time.
Thanks, Tony. I hope that in this video we've helped to improve your knowledge of the schedule of inspections, which, as we've seen, requires a lot of skill and experience to undertake successfully. See you soon.
See you soon.